Now we're going to discuss the topics of storage duration, scope, and dynamic memory. When I introduced functions before, I'd mentioned the concept of variable scope. Now we're going to look at that in more detail, but we're also going to introduce the topic of storage duration. So scope has to do with where a variable is known, and our options are block level and file level. Now technically, function parameters also have a scope, but I'm not going to discuss that. Storage duration has to do with how long a variable is stored in memory. The options there, according to the C standard, are static and automatic. But there's also something called dynamic memory allocation that, while not included in the C standard as one of these options, is related to these types of things, and it's also an important topic in C programming, so I'm going to discuss it as part of this overall discussion as well. When I create a variable inside a block, and remember that a block is a set of curly brackets, when I create a variable like this inside a block, it's what's known as a local variable. And it has automatic storage duration, which means that this variable comes into existence when the block is executed, and when we reach the bottom of the block, the variable goes away. So once I leave this function, I should assume that this variable x doesn't exist, even if I were to happen to know its memory address. This variable x also has variable scope. So going back to what I just said, variable is unknown outside of this function. If I don't initialize a variable of automatic storage duration, then its initial value is essentially garbage. So if I've written int x semicolon, I cannot make assumptions about what the bit pattern that's at that spot in memory represents. It might be 0, might be something else. I don't know. Sometimes we want a variable that's created inside a function to maintain its state for repeated calls to the function. So in that case, I can use the static keyword, and so these are static local variables. So the rest of it's just like I normally would have done, int y equals 99. So when I enter this function, y initially has a value of 99. That is when I enter f the first time. Then I add 1 to y to get 100, and I return 100. If I enter f a second time, y still has the value of 100 it had when I left the first time. So I add 1 to that to get 101. When I enter f a third time, now y is 101. We add 1 to that to get 102, and we return 102. So that's called static storage duration. However, y still has block scope, which means outside this function, y is unknown. Now another difference between static storage duration and automatic storage duration is that if I had not initialized y, if I'd written static int y semicolon, then the computer will give y an initial value of 0 for me. So that's when I can trust that's what the initial value would be, but not in this case, if I had not initialized it myself. Sometimes we create variables outside of all functions, and those are called global variables. They have static storage duration, just like this variable has static storage duration, which means they live as long as the program is running. But they have file scope, which means they're known from the point that they're created all the way down the file. So every function that we define along the way, that variable is known inside that function, unless we define a variable inside that function of the same variable name. And just like we saw here for this variable of static storage duration, global variables are initialized to 0 unless we give them an initial value. So let's see some examples of this. So let's look at the static local variables first. I could pass it values, I can return values, all that part's the same. I'm just making it real easy to work with. So in main, I'm going to call the f function 5 times. And when I get down here, it says create a variable a with an initial value of 1, create a variable b with an initial value of 1, but this has static storage duration, print the current values, and then add 1 to each. Oops, what did I leave out? Expected. Right there. So on every call to f, it's a brand new day for variable a. It's like it never existed before, and so it always has an initial value of 1. By the end of the function, it has a value of 2, but since we don't do anything with it, we lose it. B has an initial value of 1, and it's actually created outside of all this, so it never technically gets initialized when f is called, but that doesn't really matter for our purposes. But the first time I call f, b has a value of 1, so I print that. Then I add 1 to it to get 2, so when I call again, we just pick where we left off. So b now is 2, b is 3, b is 4, b is 5. I've personally never had a lot of use for static variables, but they can be beneficial in certain situations. So let's look at this. So I'm going to perform tokenization. Let's fix these. So let's see what happens. This is a string. So I just tokenized that. So you may recall from my string library functions video that the way string toke works is I call it the first time by giving it the address of the null terminated array of characters. So I can't use a string literal for this because it's going to make changes. But I can change this, so I give it that plus the address of a string containing the delimiters. That is the thing that separates the tokens. So I want to get what I consider the words. So what happens the first time it calls this is it finds this, sees that space, because that's what I define here, and puts a terminating null there. When I call it the next time, I want to pick up where it left off, which is for the is. So I put a null here. So it returns the address of the I and is and puts a terminating null here. Called it the third time, it returns the address of A and puts a null here. And then the fourth time, it returns the address of the S, and there's already a null here. So we're basically done. So additional calls to string toke would actually return null. But the question is, how does this second call to string toke know where to pick up at? How does the third call know where to pick up where it left off? How does the fourth call know where to pick up? Well, if you look at implementations of string toke, you'll see they have a variable defined like this. And I guess in their case would be probably something like this. So they have a static variable that stores the address of the next token. So each additional call, when I put null in there, just looks at this variable and says, oh, you want me to pick up where you left off since you didn't give me a new address to start at. So I'll just use the one I saved and work my way through. So it's using a static variable. I've never seen implementations of the fgetString function to see how they're actually coded. But if you look at how it's used, each time I call it, I get a new line from a file. So I would have to assume they also have a static variable inside it that keeps track of where it left off. So I don't know how you would do those things without static variables. I mean, I guess I technically do know. Whoever wrote string toke, if they didn't use static variables, could force the person using string toke to store the address of the next token themselves in some way. But that'd be somewhat painful. So it's much better to do what they've done, which is take care of saving what they need themselves. Looking more at block level scope, you may think it's fairly simple. I just create a set of curly brackets, create some variables inside, and that's where they're known at. But we can nest those sets of curly brackets. So here I have two ints, A and B, with initial values of 10 and 20 respectively. I print those, so it's at level 1, so I see 10 and 20. But then I create a nested block, so it's inside this block. So here I create another variable A with initial value of 300 and a brand new variable called C with initial value of 400. So when I say print A, B, and C, we see 300 instead of 10. We see the 20 from before because I didn't say anything about a new B, and we see the C that I just created. Now we leave that block, so I say print A and B, and A is returned to 10, and B is still 20. Now at this point, if I were to uncomment this line and try to print C, because this is an automatic variable and has block scope duration, well then it would be unknown here. So I would actually get a compilation error if I tried to print C. So now let's talk about dynamic memory allocation. So up till now, when we create an array, we had to know how much memory to allocate at the time that we wrote the program. So maybe we did something like this. So variable F, void F, void. I'm just going to put all the code here. It's D, and I had to hard code 5 if that's what I wanted. And I could have given it initial values, but maybe I want to fill it in with something else. But this allocates memory for an array of 5 ints. And because this is an automatic variable, it comes into existence when this function is called, and it ceases to exist when this ends. But what's at issue here is the fact I had to know about the 5. So what if I said, well, I don't know how much memory I need, but it won't be more than 1 million numbers. Well, okay, I guess I have to put 1 million in here, which potentially wastes a lot of space. So how can we deal with that? Well, if you're using C99, then you could do something like this. And that would work. But this isn't C99. We're talking about C89, so I can't do that. So how do we do the equivalent of that? Well, that's what we're going to talk about now. It turns out that I can request memory from the operating system, and then if it meets my request, it will give me back the address to a block of memory. And doing this is called dynamic memory allocation. Now in this example, I talked specifically about arrays, but as we move forward and start to learn to construct data structures, we'll see that we'll use this a lot to produce structures on the fly. So instead of me having to hard code the creation of a structure, maybe I have a loop that runs an unknown number of times at the time I'm writing the code. Maybe I prompt the user to say, well, how many times do you want the loop to run? And on each iteration, I produce a brand new structure. So that's the type of thing we'll do later. So what are some of the pros of dynamic memory allocation? Well, as I just said, I don't have to know in advance how much memory to allocate for that. So it gives me more flexibility in my memory usage. Because if I said, well, my array might need anywhere from 5 to 1 million numbers, well, that's a pretty big range there to be allocating memory for. And if it turns out I only need to store 10 numbers, I just wasted a lot of space. Another problem is if I did what I just had, I think I erased all the code when I had this. Let's say we do some stuff, so I'll do some stuff here and here and here. But at this point, I'll put this in here. I no longer need that array, but I still want to do a bunch of stuff. I can't free up this memory. It exists as long as this block exists. And if this program is some program that runs for weeks at a time, that means this memory is allocated for weeks at a time. There's nothing I can do about it. So one of the benefits of dynamically allocated memory is that I'm able to free up the memory once it's no longer needed, which makes it available to other programs. So what's the downsides of dynamic memory allocation? Well, I have to use pointers. The functions that I call to request a block of memory will return the address to a block of memory if they're able to meet my request. So I have to store that in a pointer. And whenever you have pointers, you have the opportunity to mess pointers up. That's just the nature of the beast for pointers. I've said before that one of the benefits of dynamically allocated memory is I'm capable of freeing up the memory when needed. Well, it turns out as the programmer, you're actually responsible for freeing it up. In this example I had here, when we get to the bottom of the block, because this is automatic storage duration, this is automatically freed up for us. I don't have to remember to free it up. But when I'm using dynamic memory allocation, I have to remember to free it up at the point where I'm able to do so. If I don't do that, and the program keeps going, then we create what's called a memory leak. And browsers for the internet are notorious for having memory leaks. You may have noticed that the longer you run your browser, the more memory it consumes. Now, a lot of that is also because the cache is keeping track of web pages that you visited and things like that. But I at least suspect that a lot of the usage is just due to memory leaks. So the functions that we'll use to perform dynamic memory allocation are these: Malik, Calloc, Realic, and Free. Malik and Calloc are both called to request a block of memory. Now, in the case of Malik, you give it the total size in bytes that you want. So if I want to store 25 ints and each int is 4 bytes, then somehow I need to put the number 100 in here. Now typically I wouldn't hard code 100. I would use some formula to calculate that, because maybe I'm determining the size or the number of elements in the array on the fly. So maybe I don't know it's 100 at the time I'm running the code. So somehow I get that number in here. If Malik's able to meet my request, it will return the address to the beginning of the allocated memory. If it can't meet my request, it returns null. But one thing to keep in mind is that it does not initialize that block of memory. So just like what I showed here, I've allocated memory for 5 ints, but they're garbage values. I didn't specify what the initial value should be. So if I need to do something about that, then I do so. Calloc needs similar information to what Malik does, but breaks it up into parts. So whereas here I was thinking, 25 ints is 25 times 4 is 100 bytes. Calloc wants you to put the 25 here and the 4 here. And then it also returns the address of a block of memory or null if it can't. But the other difference between Calloc and Malik is that Calloc will initialize your block of memory to 0. So it would be similar to doing this, where I've initialized those values to 0. Both functions return a pointer of type void star. So that's considered a generic pointer, so it really doesn't have a real type, because it can be used to create an array of ints, or array of doubles, or array of chars, or array of pointers to ints, or whatever. At some point, the address needs to be converted to the appropriate type, and we'll talk about that here later, but this is what it actually returns. So we said that variables of automatic storage duration disappear once the block they're creating ends, and variables of static storage duration exist as long as the program is running, so they never go away while your program is running. In the case of Malik and Calloc, that's not how things work. So memory that's been allocated using Malik or Calloc only goes away when either the program itself comes to an end or the programmer explicitly frees the memory. And to do that, they call the free function, giving it the pointer to the block of memory that you want to free. And so as I stated earlier, not calling free, but letting the program continue to run, and that memory not being needed anymore produces what's called a memory leak. Another function we'll use is called Realic. Sometimes we allocate a block of memory, and then at some point we realize that the block of memory needs to be larger or it needs to be smaller. And to change the size, to grow it or shrink it, we can call Realic. So Realic needs the pointer to the existing dynamically allocated memory. I couldn't use it here because this isn't dynamically allocated. It would need the pointer to the existing dynamically allocated memory and then the new size in bytes. So if I had a block of memory that was 100 bytes in size and I wanted to double its size, I would give the pointer to that block of memory and then 200 here. And so like Malik and Calic, Realic either returns an address to the beginning of the allocated memory or null if it fails. So let's look at an example of using Malik. Malik and the other functions we just discussed are stored in standard lib. So here I create a variable I that's an int. I create a pointer to an int called d. And now here I'm going to call Malik, and I want it to give me enough memory to store 5 ints. I wrote size of int because remember the standard technically says that an int has to be at least 2 bytes in size. So even though modern computers, as far as I know, all use 4 bytes, older computers used to use 2 bytes. So this would actually be the more portable way of writing this. And then when I assign this to D, the void star that this address has will get converted to int star. Now if you look at older code that uses Malik, you'll see an explicit cast. So it might have said D equal parentheses, int star, close parentheses, Malik, and the rest of this. There's arguments to be made for doing it that way, and there's arguments to be made for not explicitly doing it. I've always done this, but some people prefer the other. But also notice something else here. I'm treating this block of memory as an array of 5 ints, just like I did here. And to access those elements, I just write d sub I. Because remember, if you've seen my video that talked about the relationship between pointers and arrays, and I talked about pointer notation, we know that this, which is subscript notation, just gets turned into something that looks like this. D plus I, and actually it would be dereferenced. So it takes the address stored in D, calculates an offset using pointer notation for the I, and it dereferences the new address. So this works the same way. I give it that address, add in my I, and because D is of type int star, it knows how to do the pointer arithmetic correctly, which is also why if I were to mistakenly call this double star, it wouldn't work the way I need it to work. So it still matters what size you put in here or what type you use. So this program just allocates the memory, populates the memory in this way, prints out the values, and then frees up the memory. So now going back to the example before where I said, well, how could we possibly know how much memory to allocate? We could do this. Give it in. So now we'll say int in. And we'll do this. And times size of int. Sorry. And we'll give it some initial values. And we also can do this now as well, which we couldn't do before. Int star. So I need to. Oh, we'll do this. Sorry, I'm making this up on the fly, so I'm thinking of every variable that I need. And now we'll have something like this. Oops, sorry, this needs to be this if I'm going to do this. I'll just fix it here. I think that's all right. There's mine. So I did this so I wouldn't have 0 times 10 the first time. So this will go from 1 to 5 inside the parentheses. So that gives me 10 to 20. And you can see, because this is dynamically allocated memory, even though these variables, including D itself, the variable D that stores the address of the block of memory, it disappears when the block ends. Because remember, D has its own address, but the block of memory lives on. And so I return that address, which I store in P, which means now that I'm through using it, I need to say free P. I mean, technically the program freed it up when it ended, but that's a good habit to get into. And that's what happens. So I allocated memory here. Dynamically, I returned the address to here, and I stored it. What if I hadn't done that? What if I had done this? Whether or not I have 5 in here or not, doesn't matter. So you say, well, D has an address. I'm going to return the address of D. And actually writing, well, I have a couple options here. Writing D also gives me the address of the first element of the array. So this will be of type int star. So it's the correct type. But this still has automatic storage duration. So this is going to be a problem, as the compiler will warn me about probably. Yeah, warning, function returns address of local variable. It's telling me don't do that. But let's see if it even created it. So let's remove a.out just to confirm. So see, it does compile. It's just a warning. I say just a warning. You should take warning seriously. But see, it didn't like that, because for all intents and purposes, this block of memory that stores these 5 numbers doesn't exist anymore. Or at least I don't have access to it. So I shouldn't do this. If you want to do it, use Malik, like I showed before. So there's lots of things you can do with dynamic memory allocation, but I'll create separate videos for those things because this video is starting to get long. But let's look at one last thing. So where are these things stored? We talk about automatic storage duration and static storage duration and things like that. Where are they stored? Well, technically, the C89 standard doesn't specify where they have to be stored. That's really a decision to be made by the people who write compilers in the operating system. But I will tell you that the way it's normally taught, which I think conforms to many modern computers, certainly PCs, matches up what I'm going to tell you here. So automatic variables, that's like this right here. So let's go back and look at some things. Doesn't matter about this. So int x equals 5. So that's an automatic variable, or has automatic storage duration. Static int y equals 10. Static storage duration. Char star s equals, this is a string literal. If you haven't seen my video on strings, we discussed this there, right? And these are automatic duration and stuff as well. So everything down here is automatic duration, but these are some other examples. And then also, since we talked about global variables, int z equals 99. That has static storage duration. So looking at this, where are things typically stored at? So automatic variables, like int x here, int I, int n, are stored on what we call the stack. Dynamically allocated memory is stored in the heap. That's the ones that use Malik, which I don't have here. But if we use Malik, or Calic, or Realic, those are all stored in what's called the heap. And then string literals and static storage duration variables have to be stored somewhere because they exist as long as this program runs. There's no way to get rid of them. So they're actually stored in a third place. And once again, that's sort of a compiler / OS decision. I think more of a compiler decision, really, or a compiler writer. So this is sort of the basic idea, but let's talk a little bit more about the stack while we're here, because that's an important concept. So we'll need to revisit the concept of the stack. So let's first distinguish between a stack and the stack. Right? So when we talk about a stack, we're talking about something that's called a data structure. And if you're a computer science major, then you probably have to take a course with a title of either data structures or data structures and algorithms or something like that. So data structures have to do with different ways we might represent things in memory that has certain pros and cons. So certain data structures make it easier to find information. Other data structures make it easy to insert things between adjacent elements. For example, if we have, an array created in the normal sense, these are contiguous memory locations. So let's say this has 1 and 3 and 7 and 8 and 9. And we're not using this spot. Right? Well, let's say that I get the value of 2 because I want to keep this sorted. So I need to insert 2 between the 1 and 3. So how do I do that? Well, I have to move the 9 over to here, and then move the 8 over to here, and the 7 over to here, and the 3 over to here, and then I can write the 2 right here. Well, if this array had 1 million or 1 billion elements, that takes a lot of work. So there's data structures that would actually allow me to do the insertion with very little work because of how they actually tie everything together. But that's for another course. Now when we talk about the stack, we're going to talk about the fact that when you buy a computer, it comes with memory, right? So when you bought your computer, maybe it was advertised as having, 8 gigabytes of memory or 16 gigabytes of memory or something else, because I'm talking about this in the year 2020. And so that's all your memory. But when you run your program, the operating system gives that particular program a small segment of your available memory, because you have other programs running as well, and they each get their own little segment. So that segment is broken up into smaller parts. And so this is one layout that you'll commonly see. So the program itself has to be stored somewhere. And so that's, I think, called the code section. And this would be the actual programming code, the programming logic. And sometimes there's a data section. These are implementation dependent things. So this isn't set in stone. But you might have this data section. And then typically we might have the heap, which I mentioned for dynamic memory allocation. And it grows in this direction. And then we have the stack. And it grows in this direction. So they grow towards each other. And one of the benefits of doing this is that if I want them both, say, to grow down, because these have memory addresses, well, then I have to make a decision. If I say I'm going to split right here and put the heap here going down, well, what if the heap only uses a little bit of memory and the stack needs to use a lot? Well, now I've limited stack and wasted space for the heap. If they grow towards each other, well, then essentially the dividing line between how much memory they each use up can move up and down to different positions. So anyway, let's talk about the stack. So let's say I have this program, and I'm going to simplify what I write here to save some space and time. But we have main, and in it I create a variable x, and we give it a value of 1, and so this would be int x or whatever, but I'm saving space and time again. And then we call a function a. And then maybe when we get back, we do something with x, so x++. Close it main. Now we get to a. This creates a variable y, value of 2. We call function b. Get back. Y does something, y++. Close this up. And we have function b. This says variable z equals 3 initially. Close it up. So how does this work? Well, the logic says create a variable called x, call function a, the programming flow jumps down to here, create a variable y, call function b, the flow jumps down to here, create a variable z, do some stuff with it, return to where we left off, reuse y, which was created here, we're at the bottom of the block, return where we came from here, use x, when we hit the bottom of this, which is main, our program comes to an end. But how does the computer keep track of all this? So a stack is called a last in, first out data structure. So the most common analogy for what a stack is like the plate dispenser at a buffet. You see the top right here, which you see a plate. But underneath this was another plate, and underneath was another plate, and another plate. So which plate was put into the stack first? Well, this one. And the one that was added second was this one. And third was this one. And this is now the fourth plate. So if I want to get to plate 2, then I have to remove plate 4 and plate 3. So the last in were the first to come back out. I added plate 4 last, but I removed plate 4 first. That's how this works. So your stack, and now I'm going to draw it the opposite direction of this, working up. Here's main, or we'll write main out here. And so we created a variable called x and gave it a value of 1. And then with a stack, we can push things onto the stack or pop things from the stack. So now I want to call A. So I push information about A onto the stack. So now we have y equals 2. But then we call B. So I'll push information about B onto the stack. Z equals 3. So why am I doing all this? Because when I leave B right here, I need to know where I left. This is stored in memory somewhere, but I don't know where at unless I save the address for this function. And in fact, I need to save the address for where I left, which is really here. So that's stored here as well. And likewise for A, when I end it and need to go back to where I called A, I need to know where I left main. So that has to be stored somewhere here. So each time I'm pushing these things onto the stack, and then there's something, normally written SP, but that's the stack pointer. So then when I finish B and need to go back to A, I pop B from the top of the stack. But we don't really remove what's here. Instead, the stack pointer moves down here. So if the code needs to push something else onto the stack, it just overwrites this to save time. There's no reason to erase it, just overwrite it. And so the stack is what's maintaining the states for the functions each time that we left, so we can return to that state. Because even then I called this x is 1, y is 2, z is 3. I could have said x is 1 and it had another x here that's different than this x, another x here which is different than this x. It just needs to know what's going on, and that's what the stack's doing for me. So I'll create another video on dynamic memory allocation because there's lots of things to do with it. And in fact, most of the remaining videos I will create for C programming will probably use dynamic memory allocation.